mathematically identical to the process of diffusion is heat conduction. So in this case, suppose we look at the conduction of heat in a thin metal rod. We'll take E to be the thermal energy density at location x and time t, and we'll take U to be the temperature at the same place. To relate these, we need a couple of physical constants. So we will take rho to be the density of the material that we're looking at, and we will take C to be the specific heat. So this is a physical constant that indicates how much energy is required to raise the temperature of a certain type of mass by a number of degrees. So for instance, water has a very high specific heat, and that means that it takes a fair amount of energy to boil water. Okay, so in this case, we have then that energy is going to equal rho times C times temperature. And now it could be the case that perhaps rho is non-uniform or non-constant, and also that the specific heat is non-uniform or non-constant. And in fact, it might make sense that either of those actually depends on U. For instance, the density might decrease as the temperature increases or something like this. But those types of nonlinear equations are much more difficult. So for now, we will just assume that everything is constant and uniform. So let's see. If we look now at Fourier's heat law, Fourier looked at heating, and what he discovered is that heat flows down the temperature gradient. And so this is something that we all know from personal experience. Heat moves from hot areas to colder areas. This is an expression of the second law of thermodynamics. So more precisely, the flux is proportional to the opposite of the temperature gradient. So again, let's see. This means that flux looks like minus k u sub x in a one spatial dimension situation. So the heat equation, as it's called, is time derivative of u minus k times second space derivative of x is equal to 0. Actually, let me correct that slightly. This is going to be a lowercase k, and lowercase k here is capital K over rho c, and this is, well, let me back up. First off, it's going to be positive. Secondly, it's called diffusivity. And it represents how well heat can propagate through the particular material. So you can't call it velocity, because the velocity is going to change depending on where you are. Just like we saw for diffusion, the velocity is going to be proportional to the curvature of the underlying heat distribution. So you can't really call it the velocity, but it's a factor that tells you how rapidly heat can move through the material. So just like the diffusion constant, diffusivity has units of length squared per time. Okay, and so if we look at k equal to L squared over T, then solving for time, we see that time is L squared over diffusivity. This is what's referred to as the time scale for a region of length L. And it describes how long it takes heat to propagate through a region of that size.